So let me give you an example. If you say f function is x squared, okay? So what do we mean the mean? If in the discrete time case, it's just sum of xi, then divided by n. So this will be mean of x. Then we take the mean to apply to this function. Basically means it's squared. So it's less than the function. The function, then we take the mean. Okay. Then we have function fxi squared. Then we take the sum. Then we take the mean. Okay. This applies for any xi. So because we have a square here, it's basically sum, then square is less than or equal to n. We have n squared multiplied to the right hand side, the sum of square. Basically means the sum of square is less than n times the square of sum. So this is to apply Jensen inequality in discrete time case. Okay, you can use this result to prove this one. Now let me give you another example in continuous time. So in continuous time, I think short time, the Jensen inequality used in for time delay system is a special case. So in continuous time case, what do we mean the mean of x? It means if we take the integral from a to b, it doesn't matter if x, could be any function. Okay, let me use x as an example. Okay, the integral from x from a to b, then take an average. It's b minus a. So this is the average of x. Then we apply the f function. Still, I use fx is x squared. Okay, this square is less than the fx. So fx basically x squared. Okay, if I take a mean of it, it's basically a to b integral. The average is b a. So same thing. If I multiply b minus a squared on both sides, we have the inequality a to b x dx squared is less than b minus a. So ab x squared dx. Okay. So what I'm telling to you that you have to remember this basic form of Jensen equality, so you can use it in different scenarios. In stochastic case, x is a random variable. In determinant case, x is a discrete time variable or continuous time variable. So this is the basic form of Jensen's inequality. So lemma 1.7 is AB, two matrices may not be symmetric. Then we have trace AB transpose is less than trace A transpose, trace B transpose. I think this is some like a special case of lemma 1.1. It's a matrix swath inequality. It's like you take a trace on both sides. Take a PSA, QSB. It's very similar to swath inequality, but in the trace form. So you can extend to the P matrix, the trace A1 times AP times A1 until AP transpose is less than trace A1, A transpose, and trace AP, AP transpose. So I've not talked about the proof, so let's move on. So this result is something, if A is greater than B, greater than 0, doesn't necessarily, okay? Doesn't necessarily means trace A transpose, trace A transpose is greater or equal to trace B, B transpose, okay? So this generally is not true, okay? But it's true for symmetric matrix. If A, B, a non-negative definite symmetric matrix. So if A is greater than or equal to B, then we know trace A square is greater or equal to trace B square. Okay? So you can do this as an exercise. So I checked the answer provided by the authors. I think there are some problems about this proof. So you are welcome to develop your own proof for this lemma. So lemma 1.9 is about a matrix B is non-negative definite symmetric matrix. Then trace B square is less than trace B, then square. So if B is less than A, so we know trace B is less than trace A. So we have trace B square is less than trace A square. So last one we have this is lemma 1.10. If F is a, basically this is F in discrete time is a stable matrix. So all eigenvalues lambda n to lambda n, lambda 1 to lambda n are within the unit circle. So all the eigenvalues in unit circle in the complex plane. It's a real part, it's an imaginary part. So all the eigenvalues are in the unit circle. Okay? So basically it says if you trace Fk transpose trace. Okay, if you take the norm, then it's less than some constant C times gamma times K. If gamma is some value between 0 and 1. So you can make connection this to discrete time system stability. If you have discrete time, if xk plus 1 is f xk. So if you say x0 is x0, then you know xk plus 1, then xk plus 1 transpose. If you take a trace, okay, then you take absolute value. It becomes something like x0, then fk, then fk transpose x0. Then you have the trace. So basically the F is stable matrix. Eventually this one will become 0. And it's bound, you can bound it by something like C or K, then x0 norm. Basically this makes connections to the stability of a discrete time system. So let me stop here.